Welcome to Chapter 4, where we integrate composition-based features with machine learning models. We've learned how to generate features. Now we'll master the techniques to train accurate predictive models. This chapter covers scikit-learn pipelines, model selection, hyperparameter optimization, and interpretation with SHAP values. By the end of this chapter, you'll understand scikit-learn pipelines, model selection criteria, and the comparison between composition-based and GNN performance. You'll gain practical skills in implementing random forest, gradient boosting, and neural networks with hyperparameter optimization. You'll also master SHAP interpretation and ensemble methods for the best predictions. A remarkable finding is that composition-based models can achieve prediction accuracy close to graph neural networks that use crystal structure. In benchmarks, composition-based models achieve strong performance for formation energy, while GNNs requiring structure achieve somewhat higher accuracy. The gap is often acceptable given the significant speed advantage of composition-based approaches. Scikit-learn's pipeline class is a powerful tool that chains preprocessing and modeling steps into a single object. This ensures reproducibility, prevents data leakage during cross-validation, and simplifies deployment. We'll integrate MapMiner featureizers with standard scikit-learn components. Pipelines offer three key advantages. First, reproducibility. A single pipeline object manages all processing steps, ensuring consistent application to training and test data. Second, preventing data leakage. Cross-validation correctly fits scalars only on training folds. Third, easy deployment. Save and load entire pipelines with joblib for production use. Create a pipeline with a list of tuples, where each tuple contains a step name and a transformer or estimator object. Step names let you access components later. The last step must be an estimator. Call fit and predict on the pipeline as if it were a single model. The pipeline automatically chains the steps in sequence. Here's a complete example. Load composition data, convert strings to composition objects, generate MagPy features, split into train and test sets. Build a pipeline with standard scalar and random forest regressor. Fit on training data, predict on test data, and evaluate with MAE and R-squared. This pattern works for any composition prediction task. Different models have different strengths. Random forest is robust and interpretable. Gradient boosting often achieves higher accuracy. Neural networks can capture complex interactions but need more data. The right choice depends on your data size, accuracy requirements, and interpretability needs. Random forest is often the first choice for materials prediction. It's robust to outliers and handles high-dimensional features well. Feature importance is built-in, aiding interpretation. Key parameters are n-estimators for the number of trees, typically a few hundred, and max depth to prevent overfitting. Typical performance is good predictive accuracy. Gradient boosting builds trees sequentially, each correcting the previous errors. XGBoost and LightGBM are optimized implementations. They often achieve somewhat higher accuracy than random forest. Key parameters are learning rate for step size, max depth for tree complexity, and n-estimators for the number of boosting rounds. Regularization helps prevent overfitting. Multi-layer perceptrons can capture complex nonlinear interactions between features. The article search space covers 1 to 3 hidden layers, for example 100, 150, or 150, 150, with decreasing width. Use scikit-learn's MLP regressor for quick experiments or Keras for more control. Neural networks require more data and careful tuning, but can outperform tree methods on large datasets. Let me compare the models. Random forest has good accuracy, fast training, easy tuning, high interpretability, and works with small data. XGBoost often has the highest accuracy on tabular composition features, moderate training time, moderate tuning difficulty, medium interpretability, and needs moderate data. MLP can achieve high accuracy but has slow training, difficult tuning, low interpretability, and needs large data. Choose based on your priorities. Default hyperparameters rarely give optimal performance. We need systematic optimization. Grid Search CV exhaustively searches a defined grid. Randomized Search CV samples randomly for efficiency. Optuna uses Bayesian optimization to intelligently explore the search space. Proper optimization can noticeably improve accuracy. Grid Search CV tests all combinations in a parameter grid. Define a dictionary with parameter names and lists of values to try. Wrap your model with Grid Search CV specifying scoring and CV folds. After fitting, access best params and best score. This is thorough but slow. Multiple parameters with several values each means many combinations times CV folds. Randomized Search CV samples n-iter random combinations from the parameter space. Use scipy.stats distributions for continuous parameters like uniform or log-uniform. This is much faster for large search spaces while often finding good solutions. The randomness can actually help avoid local optima that grid search might get stuck in. Optuna is a modern optimization framework using Bayesian methods. It builds a probabilistic model of the objective function and samples promising regions. Create a study, define an objective function using trial.suggest for parameters, and call study.optimize. Optuna automatically balances exploration and exploitation, often finding optimal parameters faster. Here's an Optuna example for XGBoost. Define an objective function that creates an XGB regressor with parameters from trial.suggest int and trial.suggest float. Use cross-val score for evaluation. Create a study and call optimize with your objective and number of trials. After optimization, study.bestparams contains the optimal values. Understanding why a model makes predictions is as important as accuracy. Feature importance reveals which elemental properties drive predictions. SHAP values provide a principled framework for attribution. This interpretability connects machine learning to physical understanding and builds trust in predictions. SHAP stands for S-Hapley additive explanations based on game theory's Shapley values. For each prediction, SHAP calculates how much each feature contributed. Contributions sum to the difference between prediction and baseline. This provides both global feature importance and local explanations for individual predictions. It's model agnostic and theoretically grounded. The SHAP summary plot shows feature importance and effect direction. Features are ranked by mean absolute SHAP value. Each dot is a sample, positioned by SHAP value and colored by feature value. For formation energy, you might see electronegativity range with high positive SHAP for high values, meaning large electronegativity spread increases formation energy. The dependence plot shows how a single feature affects predictions. The x-axis is feature value, y-axis is SHAP value. Nonlinear relationships appear as curves. Color a second feature to reveal interactions. For example, atomic radius effect might depend on electronegativity. These plots provide physical insight into how elemental properties affect material properties. Implementing SHAP is straightforward. Install SHAP, import it, and create a tree explainer for tree-based models or kernel explainer for others. Call SHAP values on your feature matrix. Use SHAP.SummaryPlot for global importance and SHAP.DependencePlot for single feature analysis. Waterfall plots explain individual predictions. Permutation importance is another interpretation method. Shuffle a feature's values and measure how much prediction quality degrades. Large degradation means high importance. Use Sklern's permutation importance function. Unlike built-in importance, it's model agnostic and evaluated on test data. It accounts for feature correlations better than mean decrease in impurity. Ensemble methods combine multiple models for better predictions. Bagging, used in random forest, reduces variance by averaging. Boosting reduces bias by sequential correction. Stacking uses a metamodel to combine diverse base models. For materials prediction, stacking often provides additional accuracy improvement. Stacking uses diverse base models that capture different patterns, then a metamodel learns how to combine them. Use Sklern's stacking regressor with a list of base estimators and a final estimator. Typically combine random forest, XGBoost, and neural network as base models with linear regression as the metamodel. Cross-validation prevents overfitting in the stacking. Proper evaluation is essential for trustworthy predictions. Use appropriate metrics, cross-validation instead of single splits, and learning curves to diagnose model behavior. Compare against benchmarks to understand where your model stands relative to state-of-the-art. MAE, mean absolute error, is in the same units as the target and is easy to interpret. RMSE, root mean squared error, penalizes large errors more, useful when large errors are particularly bad. R-squared indicates the fraction of variance explained, with one being perfect. Use MAE for interpretability, R-squared for comparison. Learning curves plot training and validation error against training set size. A large gap indicates overfitting. The model memorizes training data but doesn't generalize. High error for both indicates underfitting. The model is too simple. If the curves haven't converged, more data will help. Use Sklern's learning curve function for easy implementation. Let's summarize Chapter 4. Pipeline integration ensures reproducibility and prevents data leakage. Choose random forest for robustness, XGBoost for accuracy, or neural networks for large datasets. Use Optuna for efficient hyperparameter optimization. SHAP values connect predictions to physical understanding. Proper evaluation with cross-validation ensures reliable results. In Chapter 5, we'll apply everything to a complete practical workflow. We'll fetch data from Materials Project API, build end-to-end prediction pipelines, benchmark against GNN methods, implement hybrid composition plus structure models, and work with real-world formation energy and band gap prediction tasks.